Hi, folks. My name is Miss Midha, and today we're going to focus on the following question. How can normal distributions help determine whether the results of an experiment are significant? So let's get started. All right, lots of information here. Let's go ahead and read through this together. Researchers want to know the effect of captively raising birds on the weight of the birds. The researchers begin with 100 birds divided into two groups of 50 each. One group of 50 will be raised in captivity, and the other 50 are tagged and released into the wild. After 5 years, all 100 birds are collected and weighed. There are more than 1,029 different ways to regroup the 100 birds into groups of 50 again. So looking at all the combinations would be too time consuming to reproduce. So in this case, we can run simulations to determine how the original difference in means compares to those from regrouping the data. The original groups have a difference of means of 0.27 grams, and researchers run 1,000 simulations, regrouping the data into two groups at random, and record the difference in means for the groups in each simulation. Now, this histogram right here, this histogram shows the difference in means from the simulations. Okay, one more thing to note. The researchers, they determine that the mean of the differences of means from the simulations is 0.0021 grams, and the standard deviation for the differences of means from the simulations is 0.112 grams. Okay, now what is our task for the day? We want to think about the first question here that says, what features of the distribution in the histogram let you know that modeling with a normal distribution is reasonable? After you think about that, you do want to model the simulations using a normal distribution mean of 0.0021 and a standard deviation of 0.112. After that, see if you can figure out what is the area under the curve that is more extreme than 0.27. And just a reminder, I do encourage you to use that GeoGebra app that allows you to find the area under the curve and also, of course, model the situation. Okay, now go ahead and pause the video and take as long as you need. If you need to reread the situation here, I encourage you to do so. It is a lot of information. So if you need to read it a few times to really let this sink in, definitely do that. Once you think you have answered that first question about the features and then also completed the modeling situation and finding the area under the curve that is more extreme than 0.27, go ahead and unpause the video and we'll review. Okay, so based on all of this information, what features of the distribution in the histogram let us know that modeling with a normal distribution is reasonable? Well, if we look at this, if we look at the distribution in the histogram, we can see that that distribution is bell-shaped and approximately symmetric. So knowing that information, right, knowing that this is a bell-shaped distribution and it's approximately symmetric, that allows us to know that modeling with a normal distribution is in fact reasonable. So now we need to model the simulation using a normal distribution, the mean of 0.0021 and a standard deviation of 0.112. Now, as I mentioned, the best way to do this is using that GeoGebra app. I'm going to pull it up right now. And just another reminder of where you can find it. I just have the website right here. You can just go right there and get that applet. If you're unfamiliar with what I'm referring to, I definitely encourage you to go back to videos from the previous week, in which we do talk about how to actually use this applet. But I'm going to go ahead and share my screen so we can see this again. And I'm going to key in the values that they were telling me about. Okay, so we know that the mean here is supposed to be 0.0021. So I'm just going to go ahead and key that in right here, 0.0021. And then it told me that the standard deviation was 0.112. So I have to type that in here as well, 0.112. What is the area under the curve that is more extreme than 0.27? Okay, now 0.27 is right around here. So I want to know what is the area under the curve that's more than 0.27, right? So what am I going to be looking at? I want to look at the area under the curve that is to the right of 0.27. Now, where am I going to go? Well, I'm going to click on this button right here, right? Just a reminder, that's our right-sided distribution. And I'm going to type in to this cell, I'm going to type in 0.27 because that's going to tell me x is greater than or equal to 0.27, right? All of the area that is to the right of 0.27. All right, that gives me my answer right here. I can see that it is shaded in, what part I'm looking at, and I can see that my answer here is 0.0084. Now, what does that actually represent? Okay, now, again, we know that that is, in fact, the area. So I'll actually write it on over here. I know I'm not back on the other screen, but I will write it here. That 0.0084, it is the area that is greater than 0.27 under the normal curve. Now, I know that's all this asked you, but I'm going to just sort of take it a step further. And I want you to think about how can this area be used to compare the difference of means from the simulations to the difference of means from the original group? Okay. If we think about that, how can the area be used? How can this area of 0.0084, how can this area be used to compare the difference of means from the simulations to the difference of means from the original groups? Well, if we think about it, what does this means? What is this number? I'm sorry, 0.0084. What does this number actually represent? Well, what this represents, this 0.0084, this means that approximately 0.84%, okay, that's a funny looking 8 there. I'll write that again. 0.84%, approximately 0.84% of simulations have a difference of means that are greater than 0.27. Okay, so we're pushing this a little bit further, sort of trying to think about what all of this means. Okay, so what did we do here? Well, we took the information that was given in this experiment. It was a lot of information. We figured out if the features of the distribution in the histogram that was provided before, whether that let us know that modeling with a normal distribution was reasonable. And then we went ahead and modeled the simulation using a normal distribution with a mean of 0.0021 and a standard deviation of 0.11. And we also found the area under the curve that was more extreme than 0.27.